Good day to all of you. We continue from where we left off in the last class. We were doing the controller design for a DC-DC converter from the modeling model point of view. You remember that in an earlier class we had done the controller design based on trial and error approach, and then we use the root locus technique, where the small signal model of a DC-DC converter, that is a boost converter, was taken as an example, and then the root locus was plotted, and on the root locus, which gives basically the loci of the closed loop pole locations of the entire system along with the controller, a particular pole was chosen. It's the responsibility of the designer to choose a proper pole location. This is called pole placement, and using that value of gain corresponding to that chosen point on the root locus, the gain was substituted into the system controller, and the step response was seen, evaluated, and then seen how close it was to the performance specification. So, this iteration was continued till you reach a satisfactory design. So, this is the root locus process. What we shall do today is we use ngSpice to simulate the circuit, boost converter and the controller. We shall plug in the value which we obtained in the last class and see how it performs. During implementation and also simulation, you should keep one thing in mind, that we are using the small signal model. So, if we consider, for example, the boost converter, in the boost converter we had used the transfer function V naught S by D of S, and they were all small signal models, and you had some set of zeros and poles. Now, what the small signal variables indicate is that if you are having D versus V naught, and as the D increases, let us say the V naught increases, at a given operating point D and V naught, uppercase D and uppercase V naught, indicating steady state operating point, indicating steady state. This is the steady state. So, in the neighborhood of this steady state operating point, you have small deviations, which is your D hat and V naught hat. So, the model actually is representing these small deviations in the neighborhood of the operating point, and therefore, that needs to be considered while implementing the controller design. So, we make a slight modifications, even though this has been mentioned right at the beginning at the time of modeling. I will try to restate this problem and issue. See, normally our controller, even in the trial and error approach, what we had was a comparator followed by a PI controller, let us say a PI controller, we have V naught reference and we have V naught feedback. Now, the output of the controller goes to the pulse width modulator, PWM, which actually has also another input, a triangle or a sawtooth carrier which determines the switching frequency, and then you have the driver which actually goes to the plant. And the plant can be any converter. In this case, we had chosen a boost converter. We had chosen a boost converter like this. Let me indicate it. In this fashion. So, the gate of it is actually controlled by this, and you have V naught coming in here, and this is fed back through this. Of course, there will be sensing circuitry to do that, to do the feedback portion. Now, if you look at, in the case of a switched mode converter, what we have used to design this controller is the small signal model. So, this portion should actually focus or should be the disturbance above the steady state operating point. So, in order to do that, we introduce here a feed forward term, like this, plus and plus. Let us see. Now, let us say this represents the voltage corresponding to D, and this represents the voltage corresponding to D hat. So, what you would get here is the voltage corresponding to D plus D hat. The voltage correspond to uppercase D or the steady state operating point is obtained from the steady state equation V naught is equal to V in 1 by 1 minus D. So, therefore, this is known, this is measured, which is this point, this is also measured or the reference is known. We could have what is the value. So, from here we can have V naught by V in equals 1 by 1 minus D, and therefore, D 1 minus d equals V in by V naught, and d is 1 minus V in by V naught. So, what one can do is at this point have a calculator which takes in V naught ref, takes in V in from here, this is V in, V naught ref, and calculate a voltage equivalent to D. So, this feed forward term ensures that even if this portion is not there, let us say it is 0, under steady state this will go to 0, because the steady operating point is given by this term. So, this modification has to be done in all switched mode converters, where you design the controller based on the small signal model of this, because this is supposed to only handle small signal deviations in the neighborhood of the steady operating point. Therefore, now I will try to show the boost converter in SPICE. So, this is the GEDA G-Schem or the G schematic editor, where we normally enter the circuit, and this is later on converted into a netlist, and ng SPICE is used for performing the simulation, as we did in one of the previous classes for the buck converter. So, let me zoom in onto this circuit. So, this is the regular boost converter, all of you are familiar with it by now. You have input DC voltage of 15 volts, you have the boost inductor, there is a power semiconductor switch, a diode and a capacitor, followed by a load resistance. Okay. This node point is labeled as NVS and this point is labeled as NVC. Now, this portion, this whole boost converter is the plant. Now, the control input for the plant is the gate drive, which is coming from the controller portion. So, if I zoom in the controller, you see that the control input, what goes to the gate drive NVG, is coming from the output of a PWM generator, which is having a 20 kilohertz carrier. And what I was talking about just now is this portion. See, you have a V naught reference, let us say 20 volts, you are feeding back NVC from the output node, comparator, goes through a PID. This PID value I have fixed it to what we had found out the gain, what we found out from the root locus plot in the last class. Remember that we had kept Kp is equal to 0, Kd is equal to 0 and found out Ki as 7.5. You could include in the control structure the 0 and then later on try it as homework, try to find out the value of Kp for different values of Kp and see how the response improves. But let us just try it out with what we did in the last class. Now, the output of the PID, now the PID was actually the PI controller was actually designed using the small signal model. So, these are small signal deviations in the neighborhood of the operating point. So, let us say this is the steady operating point, I am giving it from a source, constant source. You can actually put another calculation block here, sense the input voltage and the V naught ref here 1 minus V in by V naught will give you the D and corresponding voltage at this point will give you the steady state D. These two are added, which will give D plus D hat, a voltage corresponding to that, go through the PWM and gives a pulse here, pulsed output with the duty cycle of D plus D hat, which will be given to the gate of the boost converter power semiconductor switch. So, this is basically the modification that I was suggesting that we need to include, that is we need to have this feed forward term such that the controller is operating for only the small signal term, and in the steady state this portion D hat portion, voltage corresponding D hat portion will become 0. Okay. So, here as I had mentioned earlier in the other, we give actually the file name which contains the sub-circuit models of all the components. Now, this particular circuit, let us now try simulate and see what would be the voltage at the output, this 20 volt reference, and we have a 15 volts which we want it to be boosted to 20 volts as we have referred here. So, going back to the command line, let me go to that particular folder. Now, I will run ngSpice through a script file written in Octave called ngsim boost circuit dot schematic. So, when you run that, the first thing that will be done is the netlist will be generated, and later we go into the ngSpice simulator engine, which does the performs the simulation, calculates all the node voltages and the branch currents, and gives you all the possible variables which can be observed. You see that here NVC, the node which we had labeled as the output, we want to see that, and we could see NVG, the one which we want to this is basically the pulse width modulated waveform, the pulses which are given to the gate, we could see that. We could also see IL, the current through the inductor. Okay. So, one by one we could have a look at how these look like. So, if you see the voltage of NVC and the voltage V naught ref. Now, if you look at the netlist here, V naught ref is node 1. So, we could see node 1 also, V of node 1. So, you see that this is the green waveform is node 1, which is actually the reference, and the output voltage is trying to get controlled and reach a stable state. You could zoom in and try to see the nature of the ripple, calculate and study all those characteristics. We could also have a quick look at the IL waveform and the VG waveform. The inductor current waveform and the inductor current waveform and the okay, you see these two superposed. Let us zoom in so that we could. So, let me zoom near the steady state portions. So, this is the red waveform is the inductor current waveform and the green waveform is actually the pulse width modulated waveform that has been generated to achieve that steady output voltage of 20 volts. So, this pulse width modulated waveform 0 to 1 is actually the gate drive signal which is given to the boost converter switch, and you see this triangular waveform in the current waveform in the inductor as discussed in the analysis of the boost converter. Okay, so, we stop here at this point and let me go over back to the whiteboard. So, we have discussed the trial and error approach, something similar to Ziegler-Nichols method, and we have seen the other model based through the root locus technique. As I said, people have used the Bode plot technique also, that is also quite popular, using the gain and the phase margin. However, for the switched mode power converters where they are made using the three primary converters, the building blocks like the boost converter, the buck converter and the buck boost converter. The boost converter in particular has a 0 on the right of the S plane. The Bode plot is not valid, cannot be used for such non-minimum phase systems, and all the boost derivatives will not be in a position to be addressed by the Bode plot method. The root locus method is a much more general approach, and it is something similar to the pole placement approach of the state space or the modern control systems, and this can be applied even for non-minimum phase systems. Therefore, the root locus technique can be used when you know the model of the system well, when you have the small signal model or even the large signal model, and if the system is a black box, apply the trial and error method. Now, let us go forward and see what are some of the problems that we would get during implementation. Now, let us take the example of an isolated converter. Now, isolated converter are the forward converter, the half bridge, push pull and the flyback converter. Let us take one of the popular topologies like the flyback converter and see how the feedback is achieved. You remember that we were discussing while feeding back, we just drew a line from the outputs to the feedback point, but actually there is a sense circuit in between. Let us have a look at that sense circuit, so that we have a complete schematic. So, if we take the flyback converter, it is of this form. You have the flyback transformer, which is also actually an inductor, where I am using this BJT or an IGBT. You can actually replace it with MOSFET, IGBT or BJT. Now, let us say you have this drive, and this comes from the output of a PWM signal. In this fashion. Now, on the secondary side, we have just a diode and capacitance, which goes on further to other loads. Let me indicate it as a resistive load in this fashion. Very important to note that the dot polarities of the transformer are in this fashion. For the flyback, as you have studied earlier in the class. So, briefly, the operation is very simple. When this switch Q is on, you have dot as positive at V in and the non-dot end as connected to the ground, that is 0. So, therefore, this dot end is positive. This dot end would also be positive on the secondary side, reverse biases the diode, and the diode is off. The secondary side portion is off, only the capacitance is discharging to the load. So, during this time there is a current flow through this transformer, which is actually an inductor. It has an air gap inside and starts storing energy in the reluctance within the permeance. When this is switched off, the energy which is stored within is now released, starts freewheeling through the secondary. There is a reversal of polarity. The non-dot end becomes positive, this becomes positive. This will try to forward bias the diode and pump the energy into the capacitance, and thereby replenish the charge that the capacitance lost in the during the cycle when this diode was off. So, this is briefly how it operates. This is the flyback converter. And here we have the comparator, compare and control, plus minus. You have V naught reference and a V naught feedback, the output of which goes into the controller, a PI controller, which plus and plus. So, you give a voltage which is proportional to D here, and this voltage is proportional to D hat, and this will be proportional to D plus D hat. Okay. So, now all along we have been trying to say that this of course is V naught. You take V naught and feed it back here, very simple line. However, in practice we can't just draw a simple line as such like that. There are two issues. One is compatibility and another is there is this isolation. The main function of the transformer, one of the main functions of the transformer is to achieve a voltage scaling such that the load voltage becomes compatible with V in for a given duty cycle, and the other function is input and output galvanic isolation. That is also a very key important parameter to be addressed, because most of the time we would like to have an isolation of the load with the input side power and also with the control side power. Therefore, we need to interpose in between here something which does maintain that isolation and also sends across the information. So, one of the very nice ways to do that is to use an opto coupler like this. I will use a different common point symbol. Observe that these two labels or symbols are connected and this is different. Okay. So, these are galvanically separated, they are not connected together. So, it is like saying that we have a thick line wire connecting these two, but in order not to mess up the paper, we normally keep this line out and then put a symbol at this point and the same symbol at this point, indicating that these two are wired tightly together. Okay. So, the opto coupler is having the diode on the primary side and has a BJT on the secondary side, and together it is available as a pack. In this form. So, this is the opto coupler. Now, considering this kind of an opto coupler connected in this fashion, we shall introduce one more component here. Instead of connecting the voltage directly through to the opto coupler, we normally would like to protect it, allow only predefined amount of current to flow through the opto coupler. So, you need to have a resistance and allow only that much amount of opto coupler for opto current for which it is rated. And then let us say we have a resistor here and then you have some voltage which is connected across that with respect to this ground. Now, if you tap at this point and draw the signal from here. So, this signal we will call that one as V opt across R, this is R. This signal will be a measure of the output V naught. Consider the current which flows through like this, through this R opt. So, it will be V naught minus, if this is VD opt, VD opt divided by R opt will be the current that is flowing through in this resistance through the primary to this virtual ground at the output, which actually comes back here, completes the circuit. So, this is how it would be going. Now, this amount of current, once it flows through, this will bias this transistor, the opto transistor here, and it will be at some operating point, it will have some VCE. So, what appears across here would be, if this is VCC, VCC minus VCE opto. This is VCE opto. So, the voltage across the emitter resistance R is this value. So, as the voltage V naught increases, I increases, the transistor is biased more to the saturation, VCE opt decreases, and once this decreases, VCC minus VCE opt increases, or V opt across R increases. So, this value will increase. So, if V naught increases, this value increases. If V naught decreases, the current through this decreases, the transistor is biased more away from the saturation, VC opt increases and V opt decreases because of this. So, this point tries to have the same proportionality with respect to V naught and also preserving the galvanic isolation. So, this can be safely connected here. In more precise, in circuits where you need precise output regulation, the transfer ratio, the current transfer ratio of the opto coupler and the voltage across the opto coupler is dependent on temperature, especially the voltage VD opt is dependent on temperature. As temperature varies, this value varies, and therefore, the current varies, and therefore, the bias point here varies, and therefore, the output that is fed back here. So, even if the voltage here V naught has not varied, because of the temperature variation, this value would have varied, and the controller thinks that the output has varied and tries to set it to a different value. Therefore, in order to compensate for the temperature, normally another component is included. So, before that, let us clean up some of these things here. Yes. And this. So, here the new component that I am going to add is a Zener and then you connect it. Now, choose the Zener such that these two are having opposite temperature coefficient. If this is having a positive temperature coefficient, they should have a negative temperature coefficient, so that there is a compensation. Now, the current that flows through this opto would be equal to V naught minus V d opt minus V z, if this is V z, divided by R opt. So, if there is a temperature change and if this has a positive temperature coefficient and there is a increase in the a negative temperature coefficient, if there is a decrease and this has a positive temperature coefficient, there will be an increase and then that will try to compensate each other. So, this is normally put in high precision regulators in order to compensate for the temperature. So, this is how one would sense the output voltage and pass it on to the controller. Now, the next issue that would that is of worry is normally in isolated converters, just like the flyback converter that we saw, you do not have just one single output. There are multiple outputs. There may be a 5 volt output, there may be a 15 volt output, minus 15 volt output and so on. 3.3 volt outputs could have many outputs. Generally, you could have 3 to 5 outputs and you have just one control input. There is only one transistor or one BJT, IGBT or MOSFET, the gate of which can be controlled. So, therefore, only one value of duty cycle can be applied to that power semiconductor switch. However, you have multiple outputs and multiple loads. What do we do in such a case? So, let us take an example for that. Again, I am going to draw the flyback converter. So, consider this flyback converter that I am drawing here. And the secondary is like this. So, if this is V in, do not forget the dot polarities. Flyback converter has dot polarities like that. And what about the multiple outputs? What do we do or how does it appear? We would have, let us say, another output in this fashion. And that is also coupled to the same core. All three windings are placed in the same core, the primary, secondary 1 and secondary 2. So, this is just an example with 2 outputs, but there could be many more number of outputs. So, let us say this is V naught 1 and this is V naught 2. So, you have two outputs and there is only one control input, which of course goes through the drive. You have all these controllers, and I am going to just put briefly the block PWM, drive, so on and so forth. All this coming in here with a V naught reference. Which V naught reference would you give? Which is the V naught that has to be fed back from the output side? What would be fed back here, and what should be V naught reference here? Now, these are the questions. So, with one control input, you can control only either this or this. So, normally we take that particular output which is having the highest output power. That output which has the highest output power is the one which would be fed back. So, if you say that V naught 1 is going to feed a maximum output power of 200 watts and V naught 2 is going to feed 50 watts max, then this is the output that will be fed back, and take that, pass it through the opto circuit, and feed that back. Now, then what happens to V naught 2? What happens to the other output or other outputs if there are more than 2? They need to be locally regulated. The other uncontrolled outputs need to be locally regulated how? There are few methods, and one method is linear regulator method. Using switched non-isolated topology, you could use coupled inductor method, there is the magnetic amplifier method. These are some of the more popular ways by which regulation of the uncontrolled outputs are addressed. So, we shall see these possibilities, because in a practical power supply you will always find power supplies having multiple outputs. So, one by one let us take up these methods and see how it is accomplished. So, first by the linear regulator method, it is very simple. let me draw this time I will draw another converter instead of flyback. Let me draw the forward converter with demagnetizing winding. It could be half bridge, full bridge, flyback, any, just that to break the monotony I will draw some other converter. This is the topology of the forward converter, isolated, multiple outputs. Not very popular though, because of too many inductor components. I will just draw two outputs. These are the two outputs. You have the load across them, and this is the control input. Dot polarities in the forward case, the dot polarities are like that. Refer back to your class. Be careful, the dot polarity of this is in the opposite. All are on the same core, all are on the same core, and this is V in, this is V naught 1, V naught 2. So, what is the operation? When the switch is on, this primary winding is connected to ground, the dot portion is at V in, and by the turns ratio times the dot here is positive, dot here is positive, turns on this diode, forward biases, and the potential occurs across this diode is reverse biased, charges up the inductor and the capacitance, the inductor energy is building up, the inductor energy here is also building up. Now, because this dot is positive, this dot is positive, this diode is reverse biased and off. Now, this is switched off. The moment this is switched off, there is a reversal of polarity, dot end becomes negative, non-dot end becomes positive, non-dot end becomes positive here, non-dot end is positive, this diode is turned off, this diode is turned off, the inductor will start freewheeling like this, inductor will be freewheeling like this. At the same time, because the non-dot end is positive, this is positive, this will turn on this diode and put the energy into the supply. So, the magnetizing energy is pushed into the supply. So, this is the operation of the forward converter, which you already know. Now, the problem, as I was trying to tell, is how do we control the two outputs. So, depending upon the power, now let us say that this is the higher power, this is the lower power one. So, higher power let us feedback through our regular opto circuit that we discussed to the control portion. Now, for the lower power, let us do a local regulation with a linear regulator. you put a linear regulator, 3-pin fixed linear regulator, and then give it to the load. So, this would be a linear regulator, 3-pin regulator, either a fixed one like the 7-8 series or the variable ones like the LM317, those type of regulators. So, what happens is that the pulse width modulated switching converter here tries to bring the voltage here to a more compatible voltage to the output. It is only different by the amount of the regulation and this drop. So, this drop is here across the linear regulator is maintained to just minimum, so that the loss is kept minimum, and further this is a low power side. So, this linear regulator does the job of regulating this unregulated portion and thereby providing a good regulated output here. The higher power portion is automatically getting regulated because that voltage is fed back through the opto, given to the controller, which gives the proper control signal to modulate the drive duty cycle here. So, on adjusting the duty cycle here, not only does this change, this would also change, but the variation here is regulated by this linear regulator. Instead of using the linear regulator, one could use a switched mode regulator at this point. The regular buck converter, let us say, you could have a buck converter like this, another small inductor, capacitance, and the load, and you have a small PWM and a local control, and this is fed back from here, the voltage. So, this would be your PI, PWM and so on. So, this would be a local regulator based on TL494 or any other pulse width modulator, which is using the output voltage here itself as the power supply to power up all this portion of the control circuitry. So, this portion of the control circuitry is powered up by this or powered up by the regulated unregulated voltage of this at this point, and then the gate drive is supplied to the transistor, which does a buck operation here, and then appropriately you get a regulated voltage at this point. So, this is a local regulation, and that such type of locally regulated converters are basically called switched non-isolated regulator, non-isolated converters for regulating the output. So, this is the second method that we saw. The first method was the linear regulator, where this portion was replaced with a linear regulator. So, that gives you an output regulated. Instead of the linear regulator, you can use a switched non-isolated topology like the buck or the boost or the buck boost, depending upon the output that you would like to regulate here, and use that output voltage for having a local feedback control loop, which will adjust the duty cycle of this switch here and give you a regulated output. The other winding, high power winding, goes through in the same way as we had discussed till now. Okay. So, there are two other methods, the coupled inductor method and the method of the magnetic amplifier, which we are yet to discuss, which we shall do in the next class. Thank you.